All right, well, welcome everyone. Thank you so much for joining us today for our webinar Magical Mystery Tour of High Purity pH Measurements. Today we will be reviewing the theory behind the measurement of pH, discussing the issues surrounding high purity pH measurements, illustrating the difference between standard and solution temperature compensation, assessing installation requirements for successful measurements, and also clarifying good calibration and maintenance procedures. With that, I'd like to introduce our presenter, Mr. Tim Ross. Tim has been with Yokogawa for over 14 years, working in instrumentation. He has degrees from Marquette University and the Milwaukee School of Engineering. Within Yokogawa, his field of expertise includes TDLS, gas chromatograph, IR, zirconia oxygen, gas density, pH ORP, conductivity, and dissolved oxygen. And with that, I'm very excited to hand it over to our presenter, Tim. Over to you now.
Thank you, Christina. Good morning, everyone. Very pleased to be with you this morning, and I'm going to try to present as much of an interesting presentation as I can on pH. Just a little bit on the title of the presentation actually is borrowing a little bit from a gentleman from Monsanto by the name of Greg McMillan, who wrote several papers on pH back in the 70s, 80s, and they were actually quite comical. And the reason I picked Magical Mystery Tour of High Purity pH Measurements is because there is a lot of magic and a lot of mystery. So again, as Christine already hit on, we're going to review a little bit of the theory. We're going to discuss some issues surrounding high purity pH measurements. We're going to illustrate the difference between standard and solution temperature compensation. And lastly, we're going to clarify good maintenance procedures. So pH applications, anything water related can typically be measured with pH. There are lots of different reactions out there that are pH neutralizations. There's lots of product quality that is controlled by pH. pH is also related to the corrosion rate and can also be related to the growth of bacteria. In applications, we see applications throughout the world in water. Basically, you see the key up in the upper right corner there, boiler feed water. High purity pH measurements present a specific issue. Wastewater introduces several other issues that we have to deal with. Mainly the pH probes have to be constantly cleaned because they're in a very nasty environment. Pulp and paper, some very, very harsh applications in pulp and paper in the bleach plant, and black liquors and green liquors. Food, all consumables that are related to or have water introduced into their processes or use water as part of those processes are going to have a relationship to pH. Chemical, many chemical reactions require pH measurements to occur. pH. pH is defined as the negative log of the hydrogen ion concentration. It looks linear, and we see a scale of 0 to 14, but in reality, it is not a linear function. It is the negative log of the hydrogen ion. When we take and we say something is neutral, we basically are saying there are an equal number of hydrogen ions to the same amount of hydroxyl ions. If we basically have more hydrogen ions present, we have basically an issue where the solution is going acidic, such as carbon dioxide, when dissolved into water, forms carbonic acid. If we go the other direction, more OH ions being present, the solution is said to be basic above 7 pH. An example would be ammonia gas reacts with water to form ammonia hydroxide. This is a really fun slide because it helps illustrate in some realistic terms basically what different pH levels are. We've all heard the term pH balanced shampoo on commercials over the years. pH balanced shampoo, I wonder if it really was at 7 pH, but the ones I like to illustrate are my favorites, like I like beer. Well, if I do a presentation in the morning, the night before I decide to have too many beers, the way I can neutralize my stomach acid is with a little bit of a gin at 9 pH in comparison to 4. It's really not going to help much with my inebriated state or anything, but at least it'll neutralize stomach acids. Secondary thing would be my boss probably would not be too happy if I did that. At any rate, let's get back to pH. pH is the negative log of the hydrogen ion concentration. You can see a little bit of the equation down there in the lower left. The result is you have an equation where we have to establish a reference voltage, E sub 0, and then we look at the negative log of the hydrogen ion, which is affected by temperature. Well, at 7 pH at 25 degrees C, the output of the pH electrode is 0 millivolts. If I drop down to 6 pH, it goes up by 59.16 millivolts. Go down to 5, it goes down another amount of pH, by 59 millivolts. Let me get back here. The issue that we're illustrating here is that there is a temperature relationship to pH. pH is affected by temperature because the temperature affects the output of the pH glass. When we break basically the hydrogen molecule off of the water molecule, basically it weakens as temperature increases. To counter that, we're going to use a probe system that includes an analyzer, cables, electrodes, and a holder. The holder becomes very critical in high purity measurements because it must be made of stainless steel. When I look at the electrode set itself, it's always going to contain 4 different electrodes: a measuring electrode, a reference electrode, and a temperature compensator, as well as a solution ground. Basically, that probe set that you see there, the electrodes, can be put into an all-in-one sensor called a combination electrode. And that combination electrode can, at times, simplify the measurement. So it can be used depending on what the application is and where we're trying to make the measurement. This goes into a little bit more detail of the basic pH loop. And again, you see what's called basically the analyzer up on the upper left-hand side, which is actually a Flexa 402 analyzer, which is a multi-parameter analyzer manufactured by Yokogawa. You see the cable set as being an integral part, and then you see the 4 electrodes. So again, to make the measurement, I always need some type of water in solution to make the measurement, and typically needs to be greater than 5% water. If I look at the basic operation of a pH loop, you start to see some of the issues that we're dealing with. As we look a little bit closer, they become more and more defined in issues as we look at high purity water, because high purity water in and of itself does not, or is not supposed to, contain ions in it. That's the point of high purity water, to have as pure water going to a boiler system or being used in a semiconductor application to make sure that we're not basically transferring different compounds into different boiler components as they're boiled, such as in your tea kettle, or we're transferring different deposits onto a semiconductor in the case of the semiconductor industry. I won't go into the detail here because it gets into some pretty nasty circuit analysis. The reality is what you have is a voltage that is developed between the 2 electrodes. One is the reference electrode on the left, and the other one is the measuring electrode. And they're both basically silver-silver chloride electrodes. The reference electrode is immersed in a potassium chloride solution, whereas the pH silver-silver chloride electrode is immersed in a 7 buffer solution. The point is the reference probe makes contact with the solution. The measuring electrode is actually where we make the measurement. Now, there should be some issues that you should be starting to think about. Well, this is a piece of glass, you guys. So if I'm measuring the pH across a piece of glass, it's going to be difficult to measure. Here's a little bit higher detail of what happens on the glass. The glass is actually formulated to some very specific specifications. We attract hydrogen ions to basically to the surface of the electrode. That surface of the electrode basically collects the hydrogen ions, and we develop a voltage across that membrane. That membrane then puts out 59 millivolts per pH unit, depending again on the temperature. So more hydrogen ions, the higher the output of the electrode, positive. If I go the opposite direction, if I lose hydrogen ions, then basically I lose them at a rate of 59 millivolts per pH unit. If you look further into this measurement, the measurement actually gets in more detail that we can use glass for making an electrode, we can use a solid state chip for making a measuring electrode, or we use antimony electrodes. The most common is the glass electrode. There are some other solid state electrodes out there basically that utilize enamels to basically attract the hydrogen ion to them. And we also have sodium ion sensitive pH electrodes that are basically used in place of a reference probe. The main issues with the measuring electrode is breakage. Over my career, I've probably broken more pH electrodes because I didn't handle them properly. The issue is they're made of glass. If I set them on a table, they're going to roll off the table if I don't take cautions to make sure that they do not. Coating. As soon as the glass pH electrode is coated, it is going to degrade the measurement. It's going to make it harder for hydrogen ions to get to the surface of the electrode, so therefore my measurement is going to become more difficult to make. Aging. As the glass itself ages, its output will change, which will change its slope value. More on that later. Temperature. The higher the temperature, the less life I'm going to get out of the pH electrode. The reference electrode on the other side, its main purpose, remember, the measuring electrode is one half of a battery. The reference electrode is the other half of the battery. The sole purpose of the reference electrode is to make electrochemical connection with the process. We do that by taking an internal element made of silver chloride, surrounded by a fill of potassium chloride, and then we make connection to the process through a liquid junction. In some probes it will be one junction, some probes will be two junctions, and I've even seen it as many as 3 junctions, depending on what the poisoning ions are in the solution that we're dealing with. So the point is the silver chloride electrode must see ions exchanging through these junctions and into the inside. The reason we have multiple junctions is to slow down slow down the movement of poisoning ions from the process. Reference electrode life. Reference electrode life. You can expect to replace a reference electrode 3 times more than what a measuring electrode. If you're in harsh application, you could go through as many as 10 reference electrodes for every 1 measuring electrode. The issue is depending what the application is, will determine how long that reference electrode is going to last. Even after doing this many years, I get the selection of the reference electrode correct probably 60 to 70% of the time. Other times, I have to go through different iterations of reference electrodes. And you see some of them that we utilize. We'll utilize ceramic. Some people use wood. Some people use glass sleeves. Another potential is to use a flowing junction, which is a salt bridge, or what's called a Bellomatic Reference electrode. And the last one is the diffusion. You basically see 3 different probes utilizing a single junction, a double junction, and then a triple junction. A combination electrode takes all the pH probes and puts them into one small replaceable package. The probe that you see there, the combination probe you see there, is referred to as an FU20. It contains the measuring electrode, the glass pH. It contains the reference probe. It contains the ground rod. It allows us to make not only a pH measurement, but simultaneously make a ORP measurement. Another type of reference probe that's used is a Bellomatic probe. And this has become pretty much industry standard in the high purity measurements for the power industry, in that we basically use a set of bellows to create a pressure on potassium chloride, which is forced out of the electrode under constant pressure. So the silver chloride electrode is actually mounted up here inside. So process ions basically move and exchange between that silver chloride electrode through the potassium chloride. The whole purpose of the potassium chloride in the high purity application is to make contact with the measuring electrode. Without the exchange of potassium chloride, because there's very few ions present in solution in a high purity application, you must introduce potassium chloride to make the connection. It really gives us some very significant advantages, is that it makes constant contact. It adjusts for pressure changes. It gives me basically a constant flow. It prevents plugging, fouling, and poisoning of basically the electrode, the reference electrode. Another way we do it in some very nasty applications, say in the ethanol industry, where we want to measure the pH of corn mash, we'll actually use a pressurized reference electrode and a container that is filled with potassium chloride. We then basically apply a pressure to that potassium chloride container to force potassium chloride into the process slightly above the pressure of the process. So the pressure could be 55 psi. We might set the pressure of that chamber at 57 psi to make sure that we're pushing potassium chloride into solution. Reference electrode issues: coating, poisoning, stray currents, temperature, all can be issues. Coating, going back to the measuring electrode example, as soon as that reference junction gets coated over, it is going to be harder for it to make its measurement. Poisoning: any ions in solution that don't like silver chloride will eventually make their way into the reference electrode and poison the actual silver chloride. Stray current: if there's no ground solution basically in the measuring circuit, they basically, any currents in solution will find their way into the reference electrode through that junction. Temperature: just like the measuring electrode, temperature will affect the life of the pH electrode. We've hit on pretty much in a quick time period basically the overview of what pH is. And just, we know its pH is equal to the negative log of the hydrogen ion. We know that temperature affects pH, but it affects it in two different ways. One, as we've already stated, the output of the pH glass changes with temperature. Two, pH will change as the temperature changes depending on the contaminants in solution. Depending on those contaminants, we may need to compensate for it. For example, in the power industry, in high purity applications, we know, and we saw before, that Dr. Nernst basically developed the essential equation that said E, the voltage output of the probe set, is equal to the reference voltage, E sub 0, plus 0.059 times log of the hydrogen ion concentration. It's repeatable day in and day out. So all or most pH analyzers compensate for solution temperature compensation. Again, it changes with temperature. Solution temperature compensation may or may not be used. It depends on the application. What solution temperature compensation does for you in a high purity application, it compensates for the effects of temperature on the molecules themselves, not the glass. It automatically references the pH measurement to 25 degrees C. Water, we know when we look at water, as the temperature increases, the hydrogen bonds will break down more frequently. As they disassociate, the hydrogen molecule is now free forming, and I'm measuring the hydrogen ion concentration on that glass electrode. This just kind of illustrates it real briefly. If I'm at 10 pH and I start to heat that vessel up, what happens is more hydrogen ions basically disassociate. It's that disassociation that I'm going to compensate for. So it is a repeatable phenomenon. And basically I can look at the disassociation constant at 25 degrees C, and you note that it's 0 pH. But at any other point, you will see a variation in the actual dissociation constant, as well as how much it affects the pH. Just another illustration down at the bottom. If you looked at basically that point that's being pointed out in the diagram there is indicating a solution temperature compensation that will affect the measurement at a rate of negative 0.028 pH per degree C. Is it important? Yeah. Is it very important in ammonia-based treatment systems, say in a boiler application? And the answer is yes. You see two plots there. The first one is 0.5 ppm ammonia being added, and the second one is the pure water itself. Interesting, isn't that? The pure water itself actually changes the pH as the temperature changes. So you need to take a look at what is the effect, and the way you take a look at the effect is by measuring what is that solution temperature compensation. These are an example. pH1, very easy to calculate the solution temperature compensation. You measure the temperature at one temperature, 30 degrees C, and it's 9.13 pH. You measure it at a second, and it's at 50. The only key here that you want to do is those don't have to be precise values. It doesn't have to be precisely 30 and 50 degrees C. It just needs to be around 30 and at least a 10-degree differential to get a good representative value in your calculation below. All you do is throw it into the equation, and you end up with pH1 minus pH2 divided by temperature 1 minus temperature 2. And you notice you end up in this example at minus 0.032 pH per degree C. And you get the added benefit that it's basically associated and basically comparing the value to the known value at 25 degrees C. Converting back and forth from solution temperature compensation. You notice basically at 25 degrees C, there is no difference. But as you move away from 25 degrees C, you will see a change. If you move basically from one value, measured value from 25 degrees C to 40 degrees C, it's a significant difference that can be realized in the actual pH. This table was developed utilizing a pH 450 with an FU24 pH electrode from Yokogawa. The calibrated probes were left in a 9.18 buffer solution, and the solution temperature compensation is referenced to 25 degrees C. So you can use this equation to go back and forth. When you do your calibrating to a pH set, the solution temperature compensation is removed from the measurement. We've covered a lot of grounds. The issue in the last section was really just to illustrate the difference between solution temperature compensation and glass output temperature compensation. An understanding of the two helps explain some of those nuances that you may see when you're making measurements. Cleaning. Everyone over the years has asked me, well, how often do you clean my pH probes, Tim? How often should I maintain them? And I usually look at them kind of, and I try not to be too sarcastic, to be honest, but I do say, I just don't know. You have to tell me about your process, and then you have to develop your own cleaning and calibration cycle. I can tell you that boiler applications, the pH probes typically do not get that dirty. If they get a buildup on them of iron or something else, there's probably something else going on in the boiler that we're having issues with that people are going to notice much quicker than the pH actually changing and things. The point is this, is you want to establish some type of routine basis for cleaning and calibrating the probes or checking the calibration. And a lot of our different manuals can go into some of the detail on how you should establish that. The key is sometimes what I see is people are calibrating too often. If you do a calibration check or a validation check that just says, let me check my pH probes in buffer solutions and let me do it weekly. And if there's no difference greater than, say, something on the order plus or minus 0.03 degrees 0.03 pH units, then don't calibrate. Put them back into the system and just let it run. The reason I say I see people calibrate too often is when you calibrate too often, you have a tendency to hide problems that are starting to establish themselves with the pH set electrodes. Most common cleaning agent, hydrochloric acid. I even go further than this and basically say, use the weakest solution that you can to clean the pH probe. If it just takes water and a soft bristle brush to clean the pH electrode off, just use that. Even decrease your concentration of hydrochloric acid to less than 1%. If that gets the buildup on the pH probes off, fine, you're done. The only thing I want you to make sure you do is give yourself enough time to rinse the electrodes off properly and make sure that you've removed all the acids. Clean the electrodes first, use fresh buffer solutions, do a 2-point calibration. Temperature. Make certain that you allow temperature stabilization. If I take a pH probe and I pull it out of the selective catalytic reactor and that SCR happened to be at 180 degrees and I go 180 degrees C and I go and I pull the probe out and basically want to do a calibration to buffer solutions that are at room temperature, I'm going to have an issue. I must let the probe settle down. So that 180 degrees F, I'm sorry, I said C before, I basically need to let the probe's temperature settle down to the temperature of the buffer solution. Otherwise, I will be chasing my calibration. Don't do grab samples. It's much better basically to do a 2-point calibration. Make sure your probes are clean. Do not use 9 or 10 buffers, and I'll explain that statement in a minute here. Buffers. Buffers are not all equal. Mistraceable buffers is what the Yokogawa analyzers come to you pre-programmed and are expecting to see. And their values at 25 degrees C are 4.01 pH, 6.86 pH, and 9.18 pH. Now, if you use 4, 7, and 10s, that's fine. You just have to make certain that you change the calibration tables inside of your analyzer when you receive it. And does it make a difference? The answer is yes. And as you can see, the differential can be quite significant when you're talking about higher pH values. See how the temperature affects the pH of the buffer, the 9 buffers? It doesn't have as great of effect as you can see on the 4 buffers. 6, there's still some distinction in there. Why did we have different buffers? Well, the reason we have different buffers is we used to have analog meters. and analog meters had an actual meter movement that you could not read to any great significance. So what we did as manufacturers is we basically upset the calibration of the buffer solutions to give you precisely 4, 7, and 10 pHs. The key here is always make certain that you have the right buffer table programmed into the analyzer. Doing a grab sample only calibrates at one point. If you only do grab samples and you don't do a 2-point calibration, it's like a tail wagging the dog. You notice that as you move away from the calibrated value, the error between the actual pH value and the true and what is being displayed becomes more and more significant. 2-point calibration. What a 2-point calibration does is gives you and establishes both your zero and your slope of the line to match a properly calibrated instrument. Zero is also known as a symmetry offset in some analyzers. High purity water. High purity water, we want to do, if we do a grab sample comparison, what we want to do is make the measurement at the point of where the pH is coming out of the sample system. In other words, directly into the sample trays. You take a beaker, you put an overflow or flexible tube into the bottom of it, and you flow basically the sample into the beaker and let it overflow. You then make your measurement directly inside of that beaker. And the reason you're doing that is if I take a beaker of high purity water that's in the 1 to 2 microsiemen range, what will happen is if I expose it to air, it will become contaminated with carbon dioxide, which dissolves into solution, which changes the pH value. So if I don't do it at the point of measurement, I can introduce errors into the measurement as time goes on. Solution ground. Solution ground does a number of different things for me. It basically gives me the ability to do some very significant diagnostics as well as a more accurate measurement because I'm not dealing with stray currents. What it does is it gives me the ability to measure the asymmetry of that reference electrode. It gives me the ability to measure the slope of the measuring electrode. The key is it tells me things like, hey, do I have broken glass? Do I have a hairline crack? Do I have cable breakage? Do I have a faulty connection? On the reference side, it tells me if I've got a blocked junction. If the junction's being blocked over, the resistance will change and it will go up. If the resistance goes up, I can measure that and I can alarm off of that fact. So it gives me the ability to determine what's happening with my electrode sets. PH&ORP calibration diagnostics, it really helps you understand. People will always ask me, well, Tim, how do I know the pH probe is operating correctly? The only way you know that the pH probe is operating is by basically doing a calibration or a validation check to that pH probe in buffer solutions. That means you need to set up some type of routine basis for cleaning and calibrating. Barring that, if you just put a pH probe into solution and let it run, it could be running, it could be giving you good indications. It could be starting to become coated over. If it does start to become coated over, we can use the diagnostics basically to understand if the probe is going out of its tolerance values. The last issue we just talked about was talking about calibration and validation. The last thing I'll say on it is, again, you need to establish your own cleaning and calibration and validation routines on a pH probe. I can't tell you what they need to be. I can make suggestions on what I've seen over my career and things, but it's really establishing what you're comfortable with. If I'm in a plating application at Phillips Plating up in beautiful Phillips, Wisconsin, and I have a chrome destruction system where the probes get coated over daily, and they cannot run this chrome destruction system without cleaning those pH probes, then it dictates that I'm going to have to clean every 5 days. It's the simple case of the pH probe. The pH probe is going to get dirty. It's not a question, it's a statement. There's nothing anybody can do about it. We've added cleaning kits onto pH probes that help a little bit. My preference is really to push and make sure that there's a routine cleaning calibration based on what your process is. Troubleshooting. They really fall into 5 major categories: slow response, noisy, measurement drifts, incorrect measurements. And it usually relates, what I've seen over the years, it usually relates more to the reference probe than it does the measuring electrode. This is just basically a listing and giving you an idea of what you should do when you find different things. And basically it tells you clean and calibrate. That's the first thing you do with these analyzers and these pH probes. Make sure they work in pH buffer solutions. If they don't work properly in pH buffer solutions, they will not work well in your process. How do you determine that? Well, again, it's the buffers. You take the probes, you clean them up, you put them in buffer solutions. If they calibrate in buffer solutions and you have stable readings after you've cleaned and everything, then basically it's probably a process problem. If it goes the other way and you cannot calibrate, then it's probably your electrode set that's giving you issues. Which electrode do I suspect normally? I usually suspect the reference electrode is what's giving me problems. Key diagnostics. Slope. Slope looks at, and we saw that line before, we showed it. And what it's doing is it's telling me the output of the electrode has changed as that measuring electrode changes. As you can see, the illustration going basically from 59.16 millivolt output to 53.244. That's all right. It's still a good slope. It's a good slope value all the way down to about 85%. So the rule of thumb is a good slope is going to be between 85 and 100%, day in, day out. Low possible causes: the probe has just gotten old. It's been exposed to too much temperature for so long, the glass has drifted. Poisoned reference: the actual reference probe has basically been poisoned out and something's attacked the silver chloride electrode. Dirty sensor. I think that should be number 1. I should really put that number 1. Is the probe dirty? Is the probe cracked? Are the cables okay? I have seen installations in power plants where I have cables that are easily 18 to 20 years old. As those cables start to get old, they dry out and the resistance value actually changes. So if you've done everything else from a troubleshooting basis and have not checked the cables, my suggestion is check the cables. Improper calibration. You'd be surprised, maybe not, how many times we get a phone call basically saying, hey, I've calibrated my analyzer, your analyzer, Mr. Yokogawa, in 4, 7, and 10, and I have errors when I'm up around 10 pH. Well, the reason the error is because you're utilizing the wrong table inside of the actual analyzer. You need to change the table basically to a US buffer table, which is a simple pull-down menu inside the analyzer itself. Symmetry 0. What it's looking at is it's looking at, remember the equation that said E equals E sub 0 times the output of the measuring electrode, or plus the output of the measuring electrode. Well, that E sub 0 is going to change with time. And that E sub 0, I cannot make an identical reference electrode. So what I have to do is I have to compensate for, number 1, the difference in the measuring reference electrode, and as it ages. A good measuring electrode or good reference electrode is always going to have an asymmetry value of plus or minus 45 millivolts. Causes for asymmetry: aging of the electrode, ingress of the process that poisons the electrode, depletion of the internal potassium chloride solution. all can be issues. As stated before, a simple FU20, which is a combination electrode, is going to have a fixed amount of life, as is an FU24 combination electrode going to have a fixed amount of life. Whereas when I take a Bellomatic electrode, which I can refill, it's going to have additional life associated with it that I'm not going to get out of a combination electrode. Impedance values. Impedance values are in ohms. Basically, they give us a good rule of thumb. Impedance value of the measuring electrodes are in the millions of ohms. Remember when I said earlier that we're making a measurement across a piece of glass? Keep that in the back of your mind. 59 millivolts per pH unit across millions of ohms, which means there is no current. There is no current, so therefore it is a difficult measurement to make. I must have a high impedance input preamplifier into the analyzer to allow me to make the measurement. Impedance 2, which are the reference electrodes, can be as low as 2 kiloohms to 30 kiloohms. When they start to get much above that, that usually means that I'm having plugging issues occurring or coding issues occurring. Some good ideas or good things to do here. Measuring sensor cables disconnected because it's high or low, high. Measuring sensor is bad, replace the sensor. The key with pH probes, if you can't calibrate them in solution and you see these values getting out of tolerances, what you do is you replace the electrodes. Again, you try cleaning first, but the typical issue is going to be is that they've gone out of tolerance. Just wrapping up, the slope value below 85%. Hey, when you take the probe and you put it in a 7 buffer and then you put it in a 4 buffer, if it takes 15 minutes for it to stabilize, that means the probe is shot. That if you look at the reference, the slope value, you probably find that it's well below 85%. The sensor will not calibrate. The slope is out of limits. The sensor reads 7 pH in all buffers. Probe is probably cracked. Reference electrode, asymmetry values above plus or minus 60 millivolts. Response again will be slow. Asymmetry out of limits, or the resistance values are above 100 kiloohms, which is quite a high resistance for a reference electrode. What do? You replace it. Temperature. I already mentioned the issue as far as temperature. We have to watch the temperature. When we remove a probe from a process, my example before was an SCR, the probe is at 180 degrees, it's not going to last as long as it lasts in a high purity application, because in a high purity application, we've already removed most of the heat. And removed the heat in our primary coolers and our secondary coolers. So the issue on the SCR is I have to allow temperature stabilization to occur when I pull a probe out of a process. Notice it also has an effect the opposite direction. So if I have a pH probe in a waste treatment system and it is down towards 35 degrees Fahrenheit and I'm trying to calibrate with 77 degree Fahrenheit buffer solutions, I'm going to have an issue. What do? Cool a sample. What I do, basically check to make sure that there was not a solution temperature dependency that I had to correct for. pH electrodes, take a look at the probes. They're probably dirty or they're just getting old. Last one, probes can freeze, especially obviously below minus 32 degrees Fahrenheit. Electrode life, this is just relative, everyone. It's very hard to predict how long a pH probe will last. I can give you different ideas on the success we've seen with different probes and different applications. It really is driven by the application itself. Am I right most of the time? I'm going to put me being right on selection on pH probes on the length that they're going to last at probably in that 50 to 60% range, because a lot of applications you just do not know all the variables. Last couple of things here, you guys. if there's any questions inside of most, or at any rate inside of the Yokogawa series of analyzers, there are internal calibrations and maintenance logs. What I would suggest that you can utilize those, and I would actually really stress to learn how to use them, because they tell you a lot about things. They tell you the last time it was calibrated. They tell you the impedance values, impedance 1, impedance 2. It tells you the symmetry or the zero and the slope as you go through calibrations. Those are great. But what I'm going to suggest is if you're having an issue with the pH probe or pH system, set up a manual log on that pH probe and go through and write those values down with each subsequent calibration or validation. And I'm not asking you to do this basically to make work for you, but more for you to get you to take a look at what those values are as the pH probe set is changing and aging. We've taken about 45-50 minutes here to go through some of the basics of pH. We know that pH is the negative log of the hydrogen ion. We know that the more hydrogen ions we have present, the more acidic of a solution we have. The less we have, the more hydroxyl ions we have. Basically, those hydroxyl ions will cause a lower or higher pH. Basic theory. Output of the electrode is 59 millivolts per pH unit at 25 degrees C, leading to the next temperature effects. What affects the measurement? The output of the glass electrode is affected by the temperature. The process pH reading does affect the measurement. Temperature also affects the electrode life. Solution ground. I always want a solution ground in solution. Number one, to basically get rid of any stray currents, but also reduce noise and allow me to make some significant online diagnostic measurements. Maintenance. I hit on a little bit today about some do's and don'ts of calibrations. I would strongly suggest taking a look at those lists a little bit closer. And again, keeping in mind, it's you that needs to determine what your cleaning and calibration cycles are going to be on your particular probe sets. Can I help you or can I give you suggestions? Yes, I can. But ultimately, it boils back down to you. You must maintain pH electrodes. That's the key. Troubleshooting and diagnostics. If I set up a routine cleaning maintenance schedule on pH probes, they can give me many years of life associated with them as long as that maintenance is done. Typically, the problems that we see from a diagnostic basis are typically reference probes fail more often than measuring electrodes. And basically, the usual issues associated with pH measurements are going to be cleaning and fouling of the electrodes. And that wraps up and just wanted to throw out if there were any questions out there. I really appreciate everyone taking time to listening to me this afternoon. At the end of this presentation, I did list a bibliography of different articles that I have found very useful over the years. So I would encourage anyone to take a look at those documents. So Christina, any questions you would like me to address at this point?
Awesome. Thank you so much, Tim, for presenting. We did get a couple of them, so I will jump into those now. And as a reminder to anyone still on, you can continue to submit questions while we go through these. If we don't get to any of the questions you have submitted today during the live webinar, I'll have Tim answer them via email to everyone individually. But Tim, the first question we received, and I know you talked about this a little bit, is what is the typical life of a Bellomatic reference electrode?
That's a great question. You know, if I go to some of my key power plants and things, I've seen the reference electrode last anywhere from 4 years to 5 years. If you speak with Jim Perch over at Consumers Energy over in Michigan, he'll tell you basically he's seen the life of a reference Bellomatic electrode out to the 9 and 10 years as long as it's maintained. The issue is usually you do something that I refer to as a TIM, and all TIM is putting the electrode down on the desk and it actually rolls off the desk, so I end up breaking it.
Okay, thank you. Let's see. Second question is, can a Yokogawa combination FU24 smart pH sensor be used to measure high purity water?
That is an excellent question. And the answer is yes, but there's a caveat. Okay, Yokogawa just recently introduced smart pH probes, and the FU24, the caveat with the FU24 is it needs to be used with the new FLXA 402 analyzer. So the smart probe cannot be used with our older series of our older 402s or our pH 450s. So you must use the most current Flexa 402 analyzer with smart probes.
Okay, thank you. And I do know for a fact, because I was listening to you, Tim, that you talked about this a little bit, but can you touch back on how often should I clean and calibrate my pH electrodes?
That's a great one. Again, you know, and it's not to push the question off, but it's more to get buy-in by everyone on the line and things that the responsibility for that cycle is really onto you, the end user. Meaning that if, as I mentioned earlier, if I'm in a high purity application, I don't expect to clean probes very often at all. What I want to do is I want to make sure and take a look at, you know, how much, if I'm seeing any red deposits on the actual measuring electrode or I'm seeing any blackening of the reference electrode. That kind of tells me something else is getting through the process. If I go over to a waste treatment system at a rendering plant, and this is a disgusting discussion to go into, but right before lunch, but I know my pH probe is going to get fouled out with greases, gooks, junk, all kinds of different things. And that's going to dictate that I'm going to need to maintain that pH electrode every day, every other day. So there's the extremes there that you have to look at. Some pH probes in some applications, I have to go through steam sterilization in a lot of food applications, such as in fermentation processes. So again, it is dictated by the process, not by what my recommendations. My recommendations are if I've seen it and I've seen the application.
Okay, thank you. Couple more. Number 4 is, why aren't ISFET non-glass electrodes more popular?
Why are they more popular?
Why aren't they more popular?
Oh, real good. Well, an FET, field effect transistor, I actually did a lot of the testing for Leeds and Northrop back in the mid-80s on FETs, field effect transistors. And the issue is one of the boasts is we get away from the fact of using glass. Well, that's not exactly true. The field effect transistor, when we're utilizing it to make a pH measurement, is actually a silicon chip that's coated with basically silica. It's glass. However, the issue is that chip is very small. Think in the order of less than a 1/16 of an inch by a 1/16 of an inch. And that glass is the coating that they put onto it is very thin. So basically what we're doing is the number of hydrogen ions that get attracted to that surface of that chip is going to dictate what the pH is. So the issue is because it's so thin and small, it becomes very fragile. When you're using a standard glass electrode, which is the normal way of doing a high purity measurement, you have a lot of surface area associated with it. My point is this, is the FET typically is not going to last in harsh environments and will not do a good job in your high purity measurements.
Thank you. Okay, next question is it more accurate to take a pH reading at a process temp of 154 Fahrenheit or to take a grab sample and cool it?
If you wanted to look at the technical nature of it, it doesn't really matter if you cooled the sample off. It's more to the point that if you're going to be making that 150, 160 degree measurement, to do the measurement right there at the point of that you're making the measurement. the cooling of it, as long as it's cooled to a specific value, you should be all right. But then you have to worry about, did you cool it consistently to the same value? And then you have to worry about, was there any of this issue associated with the solution temperature compensation? And that you really can't tell unless you do the test. And what was the test? The test is do the calculation for solution temperature compensation by measuring the pH at 2 different temperatures and see how great a value that is. If it's very minimal, then you can ignore it. If it's not, then you need to address it.
Okay, thank you. And we have one more question, which is perfect timing. Is there a way to regenerate contaminated probes?
To regenerate contaminated probes. Not in the case of the reference probe that we spoke of, the Bellomatic electrode or the flowing junction where I have a chamber filled basically with potassium chloride. Those are really the 2 refurbishable ones. The only issues you have to watch in both of those cases is that the reference junction itself is still a ceramic plug. And that ceramic does require basically sanding from time to time. Well, here's the issue that I see mostly happen in that case. With the reference, the Bellomatic, people will basically, they're told in the instructions that they should sand it lightly every time they calibrate it. Well, be real careful how often you sand it, because you just want to hit it basically to knock off any of the buildup. As far as rejuvenating of a measuring electrode, no, there's nothing you really can do. Once the probe is aged, if you look at the actual superstructure, how that glass is made and how it's formulated with different compounds like lithium. And once those compounds are upset and dissipated, your pH probe is pretty much shot, your measuring probe is pretty much shot.
Okay, and that was actually our last question, which has us ending perfectly on time. So it looks like we've covered every question. If you do have questions that you did not get to submit today, or you think of something later, you can always email us at webinars@us.yokogawa.com. And other than that, please be on the lookout for a copy of the recording as well as the slides in your email in the next couple of days. If you have any questions, please let us know. Thanks, everyone.
Thank you, everyone.